Hello, this is Paul from Foresight Tech. In this lecture, we're going to determine whether the improper integral is convergent or divergent. We don't need to exactly go back to the definition. Okay, use the limit. If the limit exists, it means converge. If the limit does not exist, it means diverges, right? However, we have another important theorem, to tell us. Okay, so we can do the comparison. Very easy to get the answer. That we call the comparison theorem. The theorem states it's only for infinite interval, but don't worry, because later we have a remark. And this theorem also works for another type, which is a discontinuous type. Okay, what does this theorem means? Okay, if we have two functions, so we look at one function is above, another function is below. Means one function is higher than another function. In this case, how to deal with this infinite interval? Okay, how to compare the area under the curve? The first is the black one. Okay, can you see? Which means from a to infinity gx dx. So everyone you see, this is the smaller one, right? Okay, because because g is smaller than the height of g is smaller than f. Therefore, the area is also smaller than the bigger one. The bigger one is the red. Okay, the smaller one is gx. Can you see? This is easy to determine the area. Okay, so the area for g is smaller than the area for f. Okay, so now we can make a decision. If, so the first one, if f is what? It's the larger, right? F is above. F is the larger one. If the larger one convergent, what does it mean? The large one convergent means it's an exact number, not equal to infinity, right? This is not equal to infinity means the smaller one also not equal to infinity. I mean, the larger convergent, so the smaller one is convergent. Have you get it? Okay, the large one convergent means less than infinity. So the smaller one also less than infinity, which is convergent. And the second, if the smaller, the b is, if the smaller one divergent, the smaller one divergent. In easy case, divergent like goes to infinity. Okay, we pick the easy one. If this the smaller area goes to infinity, how about the large area? The large area, of course, this is greater than infinity. This approach infinity. This is definitely goes to infinity. Okay. The smaller one is infinity, so the larger one definitely is infinity. Cannot be convergent. Is divergent. So we'll go back and look at it. All we need to do is a comparison to these two functions. If g is small, okay, or we say if g is small, so the area is small, right? If f is larger, the area is larger. If the first one is if the larger one convergent, so the smaller one definitely convergent. Or if the second one, if the smaller one is divergent, goes to infinity, the larger one also goes to infinity, divergent. Okay. And this graph or this theorem shows that this is indefinite. However, we say another discontinuous type also works. Okay. We're going to a few examples. Okay. We have a few examples to show you how to do. But before we're going to the comparison, compare to which one? Okay, here is the results, the most important. Okay, this is the important results. The later or the example we compare to this very special integrand, okay, function. You know this what? This is a power function. Okay, even the power not always convergent. Let's look at the first case. This is one out of this first case. See, that's an infinite interval, right? The second case is discontinuous type. Can we look at the first? This is convergent when not all the p, the variable, only when p is greater than 1. I will show you the proof later. Okay, well, look at this integral. Look, it's very easy. However, only p greater than 1 convergent, and for all other case, divergent. Okay, and the second case, discontinuous type is just okay, go the opposite. Look at the when convergent is only p less than 1. Okay, different because the two types are different. Okay, later you will see why. Only p is very small, smaller than 1. Okay, is convergent or smaller than 1. All other cases is divergent. P greater than or equal to 1. So why? Well, look at the proof. Because this is the power functions, easy to use the definition, right? So this proof we directly use the definition. We're going to find the limits, and then we will find in this case when p greater than 1, the limit does not exist. For all other cases, the limit this exists. Okay, in other cases, the limit does not exist. Use the definition. Use the definition. How to do integration? Depends p equals 1 or does not equal 1. Okay, two cases because the antiderivative is different, right? So the first case, can we look at the first case? When p does not equal to 1, this is exactly the power, and the antiderivative is power. Okay, look at it. The limits from 1 to t. This is the definition, right? This is the power function. So the antiderivative is still power. And then find the distance between these two. The distance we're going to here. Okay, you make a little details for yourself to verify. And then we do go to here. The first step down. The second step take limits. This constant number is always exists, right? And this is a coefficient. Don't worry. What we need to do is look at the variable. The variable is t here. T goes down to the bottom. Okay. And the t goes to infinity. So do you remember this results we learned from Calc 1? We already discussed this. If the power is greater than 0, t raised to the 8th power if a greater than 0, so the bottom always go to infinity. 1 out of infinity, so the limit is what? Is 0. The limit exists. However, if the power is less than 1, less than 0, means t raised to like a negative 1's power. Okay, if we move to the top, is t raised to the 1's power. Okay, t goes to infinity, this goes to infinity. Infinity, we said the limit does not exist, right? So only two cases. We don't consider p equals 1 because here is p does not equal 1. So we look at it. When p greater than 1, the power greater than 1. So the bottom goes to infinity. This goes to 0. So what? The limit exists. So convergent. The second case, p less than 1, the limit does not, because this goes to infinity, diverges. So the limit divergence. Okay, so means this is improper integral divergent. Have you seen? The first we already determined 2. The last, which is p equals 1. Have a look at the if p equals 1 is a special case, right? And the antiderivative is what? Is ln. Okay, and then we do calculation, we get ln t. Of course, the first step we use definition. Okay, and then we look at what that is. ln function, logarithm function goes up, and then when t goes to infinity, the value of the function goes to infinity, right? Diverge, or the limits does not exist because it's infinity. Okay, and the divergent, right? This is the definition. And so we put all these 1, 2, 3 cases together, and this case is p equals 1. Okay, this case is p equals 1. Can you see that? If I put it here, all these 1, 2, 3 cases, that's all. Only one case converge. This and these other two diverge. Put the results there. Only p greater than 1 converge. Okay, this is the proof. Can we look at the second one? Proof this is very similar at this. Okay, very, very similar. You will see what is the difference. The limit is different. Okay, I will see this. We're going to prove B. See, B is totally opposite. Why? So there are two cases. Okay, two cases because the antiderivative are different. The first case, B does not equal 1. Though that power, right? Antiderivative power goes to the same one. Can you see? I think so. I made the mistake. So this is should be because to t, right? Okay, so here's not x. I should do put t. This is a t. Okay. So can we see? This time the limit is t approaches 0. Okay. T approaches 0 if p minus 1 greater than 0. Okay. If p minus 1 greater than 0, so the bottom goes to 0, right? 1 out of 0 goes to infinity. So that means in this case, if p greater than 1, okay, t goes to the denominator. The denominator will go to 0, and the delimiter will diverge. The delimiter does not exist. In this case, and the improper integral is divergent. Okay, and then we'll look at another case. If p minus 1, okay, less than 0, or p less than 1, this case, and then less than 1, you remember the negative power, okay, goes to the top, which is t raised to positive power, and the approach to 0, right? Approach 0. If approach 0, the limit exists, and the exists means converge. Okay, we determine these two cases. The third case is another. Okay, it's the same as is 1 out of x, which is the reciprocal case, and then we're going to find the limit is the limit at t approaches 0 from the right side. I think let me see. Okay, it's because 0 is discontinuous, so that's why it's positive. Okay, make sure it's not a negative. We see. Now we look at it. T approaches 0. Do you remember the graph of the function? Okay, log when t goes to 0 from the right side, it goes to negative infinity. Negative infinity, we defined it as does not exist, right? So which means diverge. Can we look at the 1, 2? This case is p equals 1. Look at these three cases. Okay, there's only one case, p less than 1, converge. Other two cases diverge. If we put it only p less than 1 converge, and the other two cases diverge. Can you see why this is different? Because the limits are different. Okay, so try to memorize these cases, and then I will use these results to comparison. For a few examples, can you see the first? So I'm going to show you how to do comparison. Okay, so first we just have a result, right? Look, at this integram is very complicated. How do you compare? Compare to what? So first, okay, we use the results we just proved for you. Compare this integral and to this improper integral to this 1 out of x raised to the pth power. What is p? Okay, determines your question. This is a little bit hard part. Okay, so how to determine p? So we look at it. We have to compare the two functions. So we take this function. How do you take that function? If I put x plus 2 over square root x 6 power minus x squared. This is the function. How do you compare to the power function? So which power? So we can reduce this. I mean this greater than, okay, this is the one. So we're going to see if someone you are familiar in calc 1, so you know this smaller part we only deal with the infinity. This smaller part we cut. I mean the x squared over here is x to the third power. I mean the x squared over x to the third power is 1 out of x. Means p should be 1. Okay, and compared to 1 out of x. But how to get there directly as this, and this greater than. Can you see the? Okay, we decrease the numerator, so this value will decrease, right? So this is smaller, and then the same. I will increase the denominator, or can you see? I put x 6. Okay, the first step is the most important. And why this is greater than this? Because the top is greater, the bottom is smaller than this. Therefore, the fraction, this is a fraction. This fraction should be greater than this fraction. The first step determine, and then simplify. What do we get? 1 out of x. This is what we just discussed. X squared over x to the third power, right, is this. The domain, so look at the domain also show these these satisfied for x between 1 to infinity, which is x greater than 1. Okay, so this is the comparison of the two integrand function. Now, which means in the theory is f and g, right? Now what do we need to do? So look at this. We compare this one, which is our questions, and to this power. Now the p equals 1. Okay, and which one is smaller? This remember. So this is smaller, right? I simply say this is smaller. The function is smaller. The integral. The integrand is smaller. The proper improper integral is smaller. So this is larger, right? So this function is larger. So the integral is larger. So now, do you remember the comparison? This is a divergent. If you're going to see, and only this case can I put it here. 1 to infinity 1 out of x dx is a divergent. What is divergent? The comparison theorem. Okay. Oh, not the results. Sorry, the results I just showed. And for this case, okay, the type 1 infinite interval is only the power p greater than 1 converge, or other case divergent, right? So this time p equals 1. Can we see? And this time, if I put a 1 out of x p, so this p equals 1. That's why it's divergent. Okay. If the smaller one divergent, the smaller one divergent, now we use the comparison theorem. Smaller one divergent, the larger one also divergent, right? So we can make a conclusion. 1 to infinity, this one, the larger one, not a 1 out. X squared plus 2 out of x6 minus x squared, which means the original, okay, in our question. This is also divergent because of the comparison. The comparison theorem. Smaller divergent, the larger divergent. Okay, so that's the first. And then the second is very similar with this. So where the most difficult part? The difficult part is the first. Okay, so how to decrease, how to reduce the function, or make a larger of the function, means how to compare these two, how to find these two. So can we look at this one? Try to build the experience. It's the same, and this is complicated, right? So what we need to do, we have to compare this one to this type. Of course, what is p we don't know. What is p we don't know. We need to find. This one is easy. Okay, so easy one to find to decrease or increase the value of the function, because the sign is less than 1, right? Okay, that's all we need. What do we need now? If I put a sine square, x squared plus 1, okay, and this integrand complicated, we don't like this, so it is less than 1 out of x squared, right? This is very easy to compare. Now we find out what is p equals 2, right? Of course, you show a little where for any variable, right? So for any x, or at least from this, for x greater than 1 belongs to the domain. What do we get? We get a comparison. We find this. So we show this is larger this time, right? This is the function larger, the integral larger. So our function is smaller. That's good, right? If our function smaller, our integral smaller, is this convergent? Definitely. Okay. Or now, what do we use the results? Is this, because we know from 1 to infinity, 1 out of x, this, the large one is convergent, right? Okay. If we go back to the results, if this p equals 2, remember this time is 1 out of x p, and the p equals 2 greater than 1, and this is exactly the case for convergent. Okay, if we have this, so we can make a conclusion. The larger one is converges, the smaller one also converges, right? So now So our integral, this is our, is a smaller one. So the smaller one is also convergent. Okay, so we get this down. One more. Look at it one more. So how to do comparison for this time? Right, we have to do comparison. So how to compare? We say this we have to compare to steer this. Okay, 1 out of x with the p's power. What is p? We need to find it out. So this time you have to try. If you use this is a smaller than 2 over x squared, so you will fail. Why? If you do another comparison, let me see. We have at least two ways. If you say this is less than 1, so this integrand is less than 2 over x squared, but that will fail. You're going to check it for yourself. No, we have to try in this way. Okay, and the second way, this is greater than 0. So it means this integram is greater than another integram. That time is exactly what we need. Can we see? 1 plus sine x squared over x squared. We say this is greater than 1 out of x squared, right? Because the top is greater. Of course, you can say equal, no problem. And for all the x's belongs to 0 to 1. But keep in mind that so we cannot go 0, right? We cannot go 0, but we can be 1. Because this is what? This is a discontinuous. Be sure this type is discontinuous at x equals 0. Okay, means this is still improper. This is improper. Remember the comparison theorem still works for this one. Okay, so don't worry, we still use. Now the top is greater than this, so the function, our function is greater than this function, no problem. Okay, which one small? This is smaller, so they are the same. And this one, our function is larger. Okay, do you remember the results? Smaller one is a divergent. This is a divergent. Okay, if we're going to check the results, we have these results: 1 out of x squared dx, and this time is still this case. Can you see? 1 out of x with the p, p equals 2 in this case. However, this is a discontinuous type. You got the results of the second results, which is b. You see, this is a convergent. Divergence. This one is divergent. Okay, totally opposite. Okay, from the infinite integral case. If this is a divergent, or I show you one more time. Can you see? Okay, so this case is the second, right? The second, if p greater than 1 is divergent. P greater than 1 is divergent. Okay. Definitely is divergent. And this is smaller divergent, so the larger is divergent too, right? Okay, so by the comparison theorem, our integral now is 1 plus sine square x squared dx is also divergent. Okay, that's all. Thank you.